The Triangulum Galaxy was never meant to be dramatic. For most of modern astronomy, it was considered the quiet neighbour, smaller than the Milky Way, smaller than Andromeda, lacking the brilliant central bulge that defines giant spirals. No confirmed supermassive black hole, no violent jets, no signs of recent catastrophic mergers. Catalogued as Messier 33, Triangulum sits roughly 2.7 million light-years from Earth, making it one of the closest spiral galaxies beyond our own. Because of that proximity, astronomers treated it as a laboratory, a place to study how spiral galaxies evolve when nothing extreme is happening. Its structure looked clean and orderly in optical images. Graceful spiral arms wrapped outward from a soft central core. Star-forming regions dotted the disk, but not in overwhelming numbers. The galaxy appeared modest, balanced, almost textbook, and that reputation shaped decades of research. When astronomers needed a comparison object for disturbed galaxies, they chose Triangulum. When they wanted to model steady star formation without the influence of a massive central black hole, they used Triangulum. It became the control case, the example of what a simple spiral galaxy should look like. But that simplicity depended on one assumption, that what we could see in visible light represented the full story. Optical telescopes are powerful, but they are limited. They capture the glow of stars clearly, yet struggle to penetrate dust. Vast clouds of cold gas and microscopic particles drift between stars, absorbing and scattering visible light. Regions rich in raw, star-forming material often appear dark or empty in optical images, even when intense processes are unfolding inside. In Triangulum, those dark regions were interpreted as quiet zones, areas where little was happening. Over time, the absence of dramatic features reinforced the idea that the galaxy was evolving in isolation, free from major external influence. It occupied an intermediate position within the local group, not massive enough to dominate, but seemingly distant enough from Andromeda to avoid serious disturbance. Its orbit was thought to be wide and slow, its disk stable, its evolution gradual. Nothing in the visible data suggested urgency. But astronomy advances not by changing the universe, but by changing how we observe it. As new instruments extended vision beyond visible wavelengths, long-held assumptions began to look fragile. Dust was no longer an obstacle. Cold gas was no longer invisible. Motion within the disk could be traced with precision rather than inferred indirectly. Triangulum had not changed. The way we were able to examine it had. And when that deeper view finally arrived, the quiet galaxy began to look less like a stable reference point, and more like a system under subtle but persistent stress. The quiet image of Triangulum began to unravel the moment astronomers questioned a simple assumption. What if visible light was hiding more than it revealed? For generations, optical telescopes shaped our understanding of galaxies. They showed glowing stars, bright nebulae, and elegant spiral patterns. But visible light is easily blocked. Dust, though thin and diffuse, absorbs and scatters starlight with surprising efficiency. Entire regions can appear dark, not because nothing is there, but because something is in the way. In Triangulum, those dark lanes were treated as empty space. The spiral arms looked thin and orderly. The outer disk seemed faint but symmetrical. Star formation appeared moderate and evenly distributed. There were no obvious distortions, no dramatic tidal tails, no violent eruptions from a central black hole. The galaxy looked stable because the brightest parts were stable. But galaxies are not defined only by their stars. Between those stars lies cold molecular gas, microscopic dust grains, and dense clouds where future generations of suns are born. These components carry most of the raw material that determines a galaxy's future, yet in visible light, they remain largely hidden. That limitation shaped decades of interpretation. When astronomers mapped Triangulum's structure, they were mapping what shone most brightly. When they measured star formation rates, they counted regions already exposed and luminous. Embedded activity, still wrapped in dust, was invisible. Subtle distortions in gas motion were averaged out, or simply undetectable. The result was a portrait that emphasized order. Triangulum's rotation curve appeared smooth. Its disk showed no massive bar structure. Its central region lacked energetic radiation. Compared to Andromeda or the Milky Way, it seemed almost understated. The absence of dramatic features reinforced the belief that it had avoided significant external disturbance. Yet there was an unresolved tension. Triangulum resides within the gravitational domain of larger neighbours. Its position in the local group places it close enough to Andromeda that some level of interaction should be expected over billions of years. And still, optical images showed little sign of that influence. The discrepancy lingered quietly in the background. Technological limits often create illusions of simplicity. When resolution is low, complexity blends into smoothness. When wavelengths are restricted, hidden processes disappear from view. In the case of Triangulum, dust acted like a veil, softening asymmetries and concealing internal imbalance. What appeared calm may simply have been obscured. Astronomers knew that to test this possibility, they would need to observe the galaxy differently. Not by collecting more visible light, but by looking beyond it. They needed a telescope capable of penetrating dust, tracing cold gas, and mapping temperature variations across the disk with precision. Only then could they determine whether Triangulum was truly evolving in isolation, or whether the signs of stress had been present all along, hidden beneath a layer of cosmic dust. When that new way of seeing finally arrived, the galaxy that once seemed simple would reveal a far more complicated reality. The answer arrived not by changing the galaxy, but by changing the instrument. The James Webb Space Telescope was not built to make galaxies prettier. It was built to see what other telescopes could not. Where optical observatories capture visible starlight, Webb operates primarily in infrared wavelengths, light that stretches beyond the range of human vision, and that difference changes everything. Infrared light passes through dust that blocks visible photons. Instead of being scattered or absorbed, these longer wavelengths slip between particles, revealing structures hidden behind dark lanes. But Webb does more than see through dust. It also detects heat. Every object with temperature emits infrared radiation. Cold molecular clouds glow faintly. Warm dust radiates softly. Young stars still wrapped in gas envelopes shine more clearly in infrared than in visible light. By measuring these signals, astronomers can map not only where material exists, but how hot it is, how dense it is, and in many cases, how it is moving. Webb's 6.5-meter mirror collects extremely faint infrared light with remarkable precision. Its instruments, including the near-infrared camera and the mid-infrared instrument, separate that light into fine detail. They can resolve individual star-forming regions, trace filaments of dust across spiral arms, and detect subtle temperature differences across tens of light years. For a galaxy like Triangulum, this capability was transformative. Optical images had emphasized stars. Webb emphasized structure. It traced cold molecular gas, the raw fuel of future stars. It highlighted embedded stellar nurseries invisible before. It exposed dust lanes not as smooth ribbons, but as turbulent networks of clumps and arcs. Infrared spectroscopy added another layer. By splitting light into its component wavelengths, Webb could identify specific molecules and measure Doppler shifts. That meant gas motion could be mapped directly, rather than inferred indirectly. Subtle shifts in wavelength revealed whether clouds were moving toward us or away from us, and at what speed. Before Webb, much of Triangulum's internal behavior had to be reconstructed from limited data. After Webb, it could be measured. Importantly, Webb operates far beyond Earth's atmosphere at the second Lagrange point. From that stable position, shielded from thermal interference, it can observe continuously without atmospheric distortion. Long exposures become possible. Faint signals accumulate. Patterns that once dissolved into noise begin to stand out. The expectation was modest. Astronomers anticipated sharper images and perhaps additional star-forming regions. They expected missing details to be filled in. What they did not expect was imbalance. As the first deep infrared maps were assembled, Triangulum no longer appeared like a quiet reference spiral. The distribution of dust, gas, and heat did not align cleanly with the stellar structure seen in visible light. Regions that once looked smooth broke apart into asymmetrical formations. Areas considered inactive showed hidden activity. The outer disk extended unevenly into space. The galaxy had not transformed. Our view of it had. And with that new vision came a more unsettling realization. The apparent simplicity of Triangulum may have been an artifact of limited observation. Beneath the veil of dust, the system was more dynamic, more irregular, and potentially more vulnerable than anyone had assumed. When the first complete infrared maps of Triangulum were assembled, the change was not dramatic at first glance. There was no explosion, no shattered spiral arms, no obvious tidal tail stretching into space. Instead, the difference emerged slowly, layer by layer, as multiple wavelengths were combined into a single coherent picture. What Webb revealed was not chaos, but imbalance. In visible light, Triangulum's spiral arms appeared thin and neatly defined. In infrared, those same arms widened into complex irregular structures. Dust lanes that once looked smooth now broke apart into clumps, filaments, and dense knots. Some regions glowed warmer than expected, while adjacent sections remained cold and faint. The symmetry that had defined the galaxy's reputation began to dissolve. One side of the disk appeared heavier, thicker with dust and embedded stars. The opposite side looked comparatively diffuse. This was not a subtle fluctuation caused by a few bright regions. The asymmetry extended across thousands of light years. Temperature maps reinforced the pattern. Instead of a gradual cooling from the center outward, pockets of elevated heat were scattered unevenly along the spiral arms. Some of these warm regions corresponded to known star-forming complexes. Others appeared in areas previously classified as inactive. The outer disk delivered an even stronger surprise. Infrared emission extended farther into space than optical surveys had indicated, tracing faint dust and gas beyond the visible spiral pattern. Yet this extension was not circular. It stretched preferentially along one direction, giving the galaxy a slightly elongated appearance. Resolution played a crucial role. Structures that once blurred together now separated into networks of fine detail. What had seemed like smooth stellar distributions broke into layered populations of older stars, younger clusters, and embedded sources. The galaxy was more crowded and more structurally complex than earlier models suggested. Importantly, there was no dominant central engine driving these irregularities. Triangulum still lacked the intense infrared signature of an active nucleus. Energy input was distributed across the disk, rather than concentrated at the core. That made the imbalance harder to attribute to internal feedback alone. When astronomers compared these maps with archival optical and radio data, discrepancies became impossible to ignore. Regions that aligned neatly in visible light diverged when dust and heat were included. Gas concentrations did not always sit directly on top of stellar spiral arms. In some places, they led the pattern. In others, they lagged behind. This misalignment suggested motion and redistribution rather than long-term equilibrium. Triangulum no longer resembled a static reference spiral. It looked like a system adjusting to forces acting unevenly across its disk. Not collapsing, not erupting, but subtly reorganizing itself. The galaxy had not lost its spiral form. It still appeared recognizable, even graceful. Yet beneath that familiar outline, the internal structure told a different story. One of uneven heating, uneven mass distribution, and subtle elongation. If Part 3 revealed that our view had changed, Part 4 revealed that the structure itself demanded new questions. The imbalance was not random noise. It followed patterns too large to dismiss. And once a symmetry appears in a galaxy of this scale, the next question becomes unavoidable. What is causing it? The asymmetry raised a deeper question. If Triangulum's structure was uneven, what was happening inside the dust where stars are born? Infrared data provided the answer. Beneath the dark lanes that once appeared inactive, Webb detected large populations of embedded young stars. These were not the bright, exposed clusters visible in optical surveys. They were protostars still wrapped in dense envelopes of gas and dust, radiating primarily in infrared as gravity compressed them toward ignition. In visible light, these regions had looked quiet. In infrared, they were alive. The distribution of this hidden star formation was not smooth. Some segments of the spiral arms contained intense pockets of activity, tightly clustered and thermally bright. Other arms of similar size showed far less embedded formation. The imbalance seen in dust structure was mirrored in stellar birth. Temperature mapping confirmed the pattern. Dust surrounding these young stars was significantly warmer than adjacent regions, even when gas density appeared comparable. That warmth indicated recent bursts rather than steady formation. Star birth in Triangulum was occurring in episodes, not at a uniform rate. This episodic behavior matters. When star formation happens in concentrated bursts, it injects energy into the surrounding gas through radiation, stellar winds, and eventual supernova explosions. That feedback alters local pressure and turbulence, influencing whether nearby clouds collapse or disperse. In a stable spiral, such processes tend to balance over time. In Triangulum, they did not appear evenly balanced. Webb also revealed a population of intermediate age clusters partially embedded in dust. These groups represented transitional stages, no longer deeply buried, but not fully cleared of surrounding material. Their abundance suggested that bursts of star formation had occurred repeatedly over hundreds of millions of years. Gas density played a decisive role. The most active hidden regions corresponded to unusually dense molecular complexes. These were not spread uniformly across the disk. Instead, they appeared compressed along specific arcs and distorted segments of spiral structure. That compression hinted at forces acting unevenly across the galaxy. Equally important was what Triangulum lacked. It has no massive central bulge and no energetic nucleus capable of regulating star formation on large scales. In more massive spirals, central feedback can redistribute gas and dampen runaway activity. Here, regulation seemed local and fragmented. Over time, such imbalance creates a patchwork evolution. Regions experiencing repeated bursts exhaust their gas more quickly. Other areas retain cold material, but remain comparatively inactive. The galaxy ages unevenly. The hidden star formation revealed by Webb did not simply increase the count of young stars. It changed the narrative. Triangulum was not quietly converting gas into stars at a steady pace. It was cycling through irregular bursts tied closely to dense, unstable gas structures. If star formation was behaving this way, the cause could not be purely internal. Something was shaping where gas gathered and where it ignited. To understand that cause, attention had to shift from the stars themselves to the raw material that fuels them, the cold molecular gas reservoirs that Webb had now exposed in unprecedented detail. If hidden star formation was the symptom, the cold molecular gas was the cause. Stars do not appear spontaneously. They form when dense pockets of molecular gas collapse under their own gravity. The amount, distribution and motion of that gas determine how a galaxy evolves. For decades, Triangulum was thought to contain a modest and fairly even supply of star-forming material. Webb showed that assumption was incomplete. Infrared observations revealed vast reservoirs of cold molecular gas embedded deep within the disk. These were not faint traces, but substantial complexes, comparable in scale to those found in larger spiral galaxies. Their presence alone increased estimates of Triangulum's total gas mass. But it was not just the quantity that mattered, it was the pattern. Instead of forming a smooth layer aligned neatly with the stellar spiral arms, the cold gas appeared concentrated into irregular clumps and elongated filaments. Some stretched hundreds of light years, others formed compact knots of extreme density. The distribution lacked the symmetry expected in a stable, long-lived spiral system. Temperature measurements confirmed how cold these regions were, often only a few tens of degrees above absolute zero. Such conditions allow gravity to dominate over internal pressure, making collapse easier. Yet the coexistence of extremely cold gas beside warmer dust and active star-forming regions suggested rapid cycling between states. Gas was not resting quietly in orbit. It was being compressed, heated, and rearranged. Many of the densest complexes were located along distorted segments of the spiral arms. In several regions, the gas did not sit directly on top of the visible stellar pattern. It was offset. That offset implied that gas motion was responding to forces beyond simple spiral density waves. Spectroscopic data added another layer of concern. Emission lines revealed turbulence inside these molecular clouds, stronger than expected from thermal motion alone. Velocity gradients suggested stretching and funneling, rather than smooth circular rotation. Some clouds appeared compressed along arcs, as though external pressure had shaped them. In galaxies, with massive central bulges or active black holes, Internal gravitational stability helps regulate gas flow. Triangulum lacks both. Its gravitational potential is dominated by its disk and dark matter halo, making it more sensitive to perturbations. That sensitivity means even modest external forces can concentrate gas unevenly across the disk. Over time, this creates localized regions of intense star formation followed by depletion. The result is not uniform growth, but structural imbalance. Dense gas pockets accelerate their own consumption. Once converted into stars, they are not quickly replenished. Adjacent regions may retain gas, but lack the compression needed to ignite it. The galaxy begins to evolve in segments rather than as a coherent whole. Webb's view of the cold molecular reservoirs made one fact unavoidable. Triangulum was not simply forming stars at a steady rate from a well-mixed supply of gas. Its raw material was being reorganized in ways inconsistent with isolation. To understand whether this reorganization was temporary turbulence or evidence of deeper instability, astronomers had to examine not just where the gas was, but how it was moving. They needed to measure motion. Mapping where gas exists reveals structure. Measuring how it moves reveals stability. In a well-balanced spiral galaxy, gas follows mostly circular paths around the center. There are small deviations caused by spiral density waves or stellar feedback, but over time those motions average out. The disk remains coherent. Webb's infrared spectroscopy allowed astronomers to examine Triangulum's gas cloud by cloud. By analyzing subtle Doppler shifts in emission lines, they could determine whether material was moving toward us or away from us, and at what speed. The expectation was simple: rotation should dominate. That is not what they found. Across multiple regions of the disk, gas velocities deviated from the smooth rotational curve predicted by stable spiral models. Some clouds were moving faster than surrounding stars, others were moving slower. In several sectors, significant radial motion was detected, gas flowing inward toward the center or outward toward the edge, rather than simply orbiting. These radial flows were not isolated events. They extended across tens of thousands of light years. In a stable system, such flows are weak and temporary. In Triangulum, they appeared persistent. The pattern was irregular. In certain arcs, inward-moving gas intersected dense molecular complexes, compressing them and triggering bursts of star formation. In other areas, gas seemed to be pulled away from star-forming zones, leaving behind depleted pockets. The galaxy's fuel supply was not simply rotating, it was being redistributed. Shear within individual clouds added another layer of complexity. Adjacent sections of the same molecular complex sometimes moved at noticeably different velocities. This internal velocity dispersion exceeded what would be expected from thermal motion or localized stellar feedback. It suggested stretching, a sign of external stress. Even more subtle were vertical motions. In several regions, gas appeared slightly displaced above or below the main plane of the disk. Such vertical heating is often associated with tidal influence. When gravitational forces act unevenly across a galaxy, they can inject energy into orbits perpendicular to the disk, gradually thickening it. Triangulum lacks a massive central bulge capable of damping large-scale disturbances. Without that stabilizing anchor, deviations in gas motion can persist rather than quickly settling back into equilibrium. When astronomers compared these velocity maps to numerical simulations, a pattern emerged. Isolated spiral galaxies rarely display this combination of sustained radial flow, shear, and vertical motion. Galaxies subjected to long-term tidal influence often do. The motions did not indicate imminent collapse. The disk was not tearing apart, but they revealed something quieter and more consequential. Triangulum was no longer behaving like an isolated, self-regulating spiral. Its most responsive component, the gas, was moving as if influenced by forces acting beyond the visible disk itself. And once motion begins to diverge from stability, the question shifts from internal processes to external gravity. And once motion begins to diverge from stability, the question shifts from internal processes to external gravity. Triangulum does not exist alone. Roughly 750,000 light-years away lies Andromeda, the most massive galaxy in the local group. In visible light, the distance appears comfortable, almost reassuring. But galaxies are not defined by their glowing stars alone. They are embedded inside vast halos of dark matter, extending far beyond what can be seen. Current estimates suggest Andromeda's dark matter halo may stretch more than 1 million light-years from its center. If that is correct, Triangulum is not merely nearby. It may already reside within Andromeda's gravitational envelope. For decades, astronomers assumed Triangulum followed a wide and relatively gentle orbit, influenced but not strongly disturbed. Optical images showed no dramatic tidal tails, no stellar bridges, no catastrophic distortion. The galaxy retained its spiral form, and that form implied independence. Webb's observations forced a reassessment. The asymmetry in gas distribution, the elongation of the outer disk, the persistent radial flows, and the subtle vertical heating all align with what simulations predict for a smaller spiral under sustained tidal stress. These are not the violent signatures of a direct collision. They are the quieter marks of long-term gravitational influence. Tidal forces arise when gravity pulls more strongly on one side of a galaxy than the other. The side facing a massive neighbor experiences slightly greater attraction than the far side. Over millions and billions of years, that differential force stretches the disk, redistributes gas, and injects energy into orbital motion. In Triangulum, the distortions show directional preference. The outer disk extends farther along an axis broadly aligned toward Andromeda. Gas concentrations appear compressed along that same orientation. Velocity deviations are strongest in regions facing the larger galaxy. Individually, each of these patterns might be ambiguous. Together, they form a consistent picture. Triangulum is responding to something beyond itself. Importantly, tidal influence does not require a close encounter. A galaxy can experience ongoing distortion simply by moving through the outer regions of a massive halo. Even modest gravitational differences applied continuously can reshape structure over time. Gas responds first because it is dissipative and easily compressed. Stars respond more slowly, retaining coherence until effects accumulate. That explains why optical images still show a recognizable spiral, while infrared data reveal deeper imbalance. The absence of dramatic stellar streams does not imply safety. It may instead indicate that Triangulum is in an early or intermediate stage of interaction. The disk remains intact, but its internal equilibrium has shifted. This reframes Triangulum's identity. It is not merely a quiet spiral evolving in isolation. It is a smaller system embedded within the gravitational dominance of a larger one. And if Andromeda's influence is already reshaping gas and motion inside the disk, the next question becomes unavoidable. Is material beginning to escape altogether? Is material beginning to escape altogether? Distortion alone does not confirm loss. A galaxy can be stretched, heated, and internally rearranged while still holding onto most of its mass. But the outer edges of Triangulum tell a more troubling story. In the faint outskirts of the disk, where gravity is weakest, Webb's infrared observations detected irregular extensions of gas and dust that no longer follow smooth circular rotation. Instead of forming a continuous envelope around the galaxy, the outer material appears fragmented and uneven. On one side, gas extends farther into space. On the opposite side, it drops off sharply. Such asymmetry is difficult to explain through internal processes alone. Velocity measurements strengthen the concern. Gas clouds in the outer regions show increased dispersion and reduced coherence in their motion. Rather than orbiting cleanly around the center, some appear marginally bound, drifting relative to the main disk. In gravitational terms, these clouds sit close to escape velocity. A small additional tidal push could remove them entirely. The direction of these irregularities is not random. The most pronounced weakening occurs along the axis facing Andromeda. This alignment supports the interpretation that tidal forces are preferentially acting on the side of Triangulum nearest the larger galaxy. Gas is the first component to be stripped because it is less tightly bound than stars. Webb's data reveal faint low-density gas structures that appear partially detached from the main disk. These wisps lack the density required for sustained star formation and display motions inconsistent with long-term stability. The stellar disk shows subtler signs. In the extreme outskirts, older stars appear more diffuse than expected for an undisturbed spiral. There are no dramatic tidal tails or luminous bridges, but gradual thinning suggests that some stars may be transitioning into loosely bound halo orbits rather than remaining confined to the disk. This pattern matches what simulations describe as tidal evaporation rather than tidal disruption. Material is not violently torn away. It is slowly peeled off over repeated passages through a massive halo. Each orbit removes a small fraction. Over billions of years, the cumulative effect becomes substantial. Another clue lies in the relationship between star formation and gas depletion. Regions that recently experienced intense bursts often sit beside areas where gas density has fallen sharply. If gas was simply cycling internally, those depleted regions would eventually refill. The lack of replenishment suggests net loss. Triangulum still retains its spiral shape. It has not suffered a catastrophic encounter. Yet the outer disk is beginning to thin, and the weakest material is being drawn outward. Stripping does not announce itself loudly. It proceeds quietly, gradually narrowing a galaxy's future. And once material leaves, it does not return. The final question is not whether Triangulum is being disturbed. It is how deep that disturbance reaches. Every galaxy is held together by an invisible foundation. Stars, gas, and dust make up only a fraction of its mass. The true gravitational scaffold is dark matter, extending far beyond the visible disk. For Triangulum, that halo has long been assumed to provide the stability needed to resist external tides. Recent evidence suggests that foundation may no longer be intact. Rotation curves at the outer edge of the galaxy show subtle irregularities. Instead of maintaining a smooth, symmetric profile, velocities fluctuate depending on direction. These deviations imply that the underlying gravitational potential is uneven. Such unevenness is difficult to reconcile with a pristine, undisturbed halo. Simulations of small spiral galaxies orbiting within the dark matter halo of a much larger host show a consistent pattern. The outer dark matter is stripped first. Long before stars are visibly torn away, the halo becomes elongated, stretched toward the dominant neighbor. Each orbital passage removes a fraction of that invisible mass. If Triangulum resides within Andromeda's extended halo, this process may already be underway. Dark matter cannot radiate energy or cool itself. Once displaced, it does not settle neatly back into place. Over time, the halo becomes less massive and less symmetric. As that happens, the escape velocity in the outer regions drops. Gas that once remained bound can drift away more easily. Stars on wide orbits become vulnerable to tidal heating. This creates a cascade. Stripping of dark matter weakens gravitational support. Weakened support accelerates gas loss. Gas loss reduces star formation. Reduced star formation alters the internal balance of the disk. Spiral structure becomes less coherent. What begins as subtle halo erosion eventually reshapes the entire system. Triangulum still appears graceful. Its spiral arms remain visible. Its disk continues to form stars. Nothing about it suggests imminent destruction, but long-term evolution does not require catastrophe. If the dark matter halo continues to erode, the galaxy's independence becomes temporary. Over billions of years, it may transition from an autonomous spiral into a gas-poor remnant orbiting within Andromeda's domain. Not through collision, not through explosion, through gradual surrender of mass. This possibility reframes Triangulum's role in the local group. It is not simply a quiet companion. It may be an example of how smaller spirals lose their identity in the gravitational shadow of giants. Webb did not reveal a dramatic event. It revealed a direction. Triangulum is not collapsing today, but its future may already be set, shaped by forces larger than itself and unfolding on timescales that make instability look like calm. What once appeared simple now carries a deeper implication. In the universe, survival is not always decided by violence. Sometimes it is decided by gravity, applied patiently over billions of years.